Okay, so what have we done so far? We have solved for f of x. Now what remains to be done? We need to solve for g of t. So now we are going to solve capital G, the time dependent part. We have solved the space dependent part. Now we are going to solve the time dependent part. So now we solve the equation 4. And what is equation 4? Equation 4 is the differential equation for the time dependent part g. So that is d2g by dt square equal to c square k times z equal to 0. And we just saw that k is equal to p square. So instead of k, I shall write p square. Minus p square. So k is minus p square. So this will become d2g by dt square plus c square p square g. And what is the value of p? P is n pi by l. P is n pi by l. So that p square will be n square n square pi square by l square. Okay, so let us look at that equation. This. So we put k equal to minus p square, and then p square is minus n square pi square by l square. Okay. So if I put c times p equal to lambda n, then lambda n becomes cn pi by l. So this equation becomes d2g by dt square plus lambda n square g equal to 0. And this is also a linear homogeneous differential equation, ordinary differential equation, and its general solution is given by gnt is given by bn cos lambda nt plus bn star sine lambda nt. Here bn and bn star are arbitrary constants, which we are going to determine using the initial conditions. Okay, here we have used gn and bn here because for each possible value of n, we shall get different values of lambda. Okay, and for each value of lambda 1, I shall get g1. For lambda 1, it will be b1, b star 1, g1. For lambda 2, it will be b2, b star 2, g2. So there are many possible solutions. For each value of n, we shall get one possible solution. So there are infinitely many possible solutions. So we have solved for f, we have solved for g. Now when we multiply them, we shall get u. Okay, so unxt would be unxt would be fn multiplied by gn. And if I write gn first, then I get this expression bn cos lambda nt plus bn star sine lambda nt multiplied by the f part. This is sine n pi by lx. So this is the term inside the bracket. This is gn. Term outside the bracket, that is f of n. And this this solutions, it can take different forms for different values of n. When n equal to 1, I get u1. When n equal to 2, I get u2. N equal to 3, I get u3. So there are many possible solutions. So these UNs, these are the solutions which satisfy the boundary conditions. And these functions are called the eigenfunctions. These UNs are called the eigenfunctions or the characteristic functions, and the values lambda n. This is equal to Cn pi by L. I repeat, the values lambda n, which is given by Cn pi by L. These values are called the eigenvalues or the characteristic values of the vibrating string. Okay, these lambda n's are called the eigenvalues or characteristic values of the vibrating string, and the set of lambdas, the set of all lambdas, is called the spectrum. It's called the spectrum. Okay, we see we see that each un represents a harmonic motion. This represents a harmonic motion having a frequency lambda by twice pi. This is like the cos omega t. This is, so let me write it here again. This term is like cos omega t. Cos omega times t. And what is omega here? Omega is lambda n. So omega n is equal to lambda n. Sorry. Omega is equal to lambda n. And omega is the angular frequency. So the frequency f would be omega by twice pi. Okay. So this gives lambda n by twice pi. Fine. Okay. And when I substitute the values of lambda n, we just saw that lambda n is, what is lambda n? Lambda n is this c n pi by L. So c n pi by L, that means this lambda n is c n pi by L. So divided by twice pi. This will become c times n by twice L. Okay. So the frequency of the vibrating string will be c times n by twice L. This is the frequency of the vibrating string. And this motion is called the end normal mode. So this motion is called the end normal mode. N-O-R-M-A-L, normal mode. So let me bring it a little down here. Okay. So let me erase this line. So end normal mode. What is the end normal mode? The solution UN. The solution UN is called the end normal mode. Okay, end normal mode, and the frequency of this end normal mode is given by c times n divided by twice L. C times n by I repeat, c times n by twice L. And this motion UN is called the end normal mode of the string. The first normal mode, that is when n is equal to 1. The first normal mode, that is when n is equal to 1. This is known as the fundamental mode. Fundamental mode, n equal to 1. So here I have shown it in a figure. This is the fundamental mode. Okay. And the others are known as overtones. Others are known as overtones. O-V-E-R-T-O-N-E-S. Overtones. That is when n is equal to 2, n is equal to 3, n equal to 4, and so on. The frequencies would be twice the fundamental mode, thrice the fundamental mode, and so on. These are called overtones. Okay. And in music study, these are called octave plus fifth, and so on. Okay. And then we just had that sine n pi x by L equal to 0. Okay. Let me show it to you here. Okay. It's not required. So here we have one term sine n pi x by L. So when will this become 0? So we have here sine n pi x by L will become 0 when x is equal to L. Here this will become 0 when x is equal to L by n. Okay. For different, and next would be twice L by n. Next would be thrice L by n, and so on till n minus 1 L by n. Okay. That means this is the end normal mode. This is the end normal mode, and this means that the end normal mode has n minus 1 nodes. This represents the number of nodes. And what are nodes? Nodes are the points of the string that do not move. Okay, if we look at the figure here, the first fundamental mode, the first mode, that is the first fundamental mode, has no node. Okay, this is the second normal mode. The second normal mode has one node here. This point is not moving. When the string oscillates, this point will not move. Let me show it to you again. Let me clear all drawings here. This is the oscillation of n equal to 2. Okay, this is the oscillation of the n equal to 2 mode. And here we see that this part will oscillate, this part will oscillate, but this node will not move when the string oscillates. And this is the third fundamental mode. The third fundamental mode has two nodes, one here and the other here. So when the string oscillates, these 2 points will not move. Similarly, the fourth fundamental mode, I repeat, the fourth fundamental mode, the fourth normal mode. I should not say fundamental mode, I should say normal mode. Fundamental mode means n equal to 1. This is the second normal mode. This is the third normal mode. This is the fourth normal mode. The fourth normal mode has, you can see it, 1, 2, 3. It has 3 nodes, NODES, nodes. Nodes are the points which do not move when the string oscillates, and so on. This will continue forever. Okay, and this is how the second normal mode oscillates. Here we have a node here. Okay, this is fine. Okay, and I just showed you, okay, I think I have erased it. Let me write it again. Okay, let me write it to you again. Here we had the frequency. We had the frequency. Okay, we had the frequency. Frequency was Cn by twice L. Cn divided by twice L. And what was the value of C? C was the constant which was given by C. C was the constant which was given by root over tension in the string divided by mass per unit length of the string. So this is frequency. Frequency is given by C. This is the nth normal mode, and can take values 1, 2, 3, 4, and so on. This is the length of the string. Okay. So how are tuning done in musical instruments? In musical instrument, it can be guitar, it can be sitar, it can be violin, it can be piano. How is tuning done? Tuning is done by changing the tension. Okay, as I said, the guitar has a knob where you can rotate the knob and increase or decrease the tension in the string. So tuning is done by changing the tension T. Here we have the frequency given by Cn by twice L, and if you increase the tension, C will increase. C will increase means the frequency will increase. If you decrease the tension, C will decrease. That means the frequency will decrease. Okay, so this is how tuning is done. But T cannot be increased indefinitely because ultimately it will break the string. So if you want a string with a high fundamental mode, I repeat, if you want a string with a high fundamental mode, what will you do? That means when n is equal to 1, we get the frequency C by twice L. And if you want the value of F to be high, what will you do? You simply increase the value of T or decrease the mass per unit length. Okay. So this may be the so this is the reason why a violin is smaller than a double bass. Okay, so this is all about tuning. Now let us move to the third part, the step number 3. Clear drawings. Step number 3, that is solution of the entire problem using Fourier series. This eigenfunctions, this given by equation number 10, this eigenfunctions, okay, un. So let me repeat what we have obtained here. What we have obtained here are the possible solutions to the wave equation satisfying the boundary conditions. We have not used the initial conditions yet. We have so far used only the boundary conditions. And how many solutions are possible? Infinitely many possible solutions are possible, each for a different value of n. When n equal to 1, we have one solution. When n equal to 2, we have another solution. When n equal to 3, we have yet another solution. So infinitely many solutions are possible to the vibrating to the equation of the vibrating string satisfying the boundary conditions. And these are plots of some possible solutions. Okay. The eigenfunctions, equation 10 satisfying the wave equation 1 and the boundary conditions. I repeat, the eigenfunctions 10 satisfy the wave equation and the boundary conditions. A single eigenfunction un will generally not satisfy the initial conditions. And what are the initial conditions? That is, the initial displacement is f of x and the initial velocity is g of x. Different parts of the string can have different initial velocities. So initial velocity is a function of x. Similarly, different parts of the string can have different displacement. So it is a function of x. So this is initial displacement. This is initial velocity of the string. But since the wave equation is linear and homogeneous, the sum of many solutions un is also a solution of equation number 1. So to obtain a solution that also satisfies the initial conditions, that is the initial conditions given by these two, we consider the infinite series. That is, we take the sum of all the eigenfunctions. Okay, we take the sum of all the eigenfunctions. That is, all possible solutions satisfying the boundary conditions. So n from 1 to infinity, we take the sum of them all. And this was the expression of un, which we had written in equation 10. So we consider this infinite series. So u of xt is the sum of all possible eigenfunctions. Now let us apply the initial condition. First initial condition, that is the given initial displacement. And what is that? When t equal to 0, the displacement was f of x. I repeat, when t equal to 0, the initial displacement was f of x. So in this equation number 12, if I substitute t equal to 0, this becomes what? Cos 0. Cos 0, this becomes sine 0. Sine 0 is 0. So this second term will vanish. Cos 0 is 1. So what remains is only bn. So bn sine n pi by lx. So bn sine n pi by lx. This is equal to f of x. So summation over bn sine n pi by lx. So this is what we obtain by using the first initial condition. So from this equation, we must choose the bn's so that the initial displacement becomes the Fourier sine series of fx. So this is nothing but the Fourier sine series of the given function f of x. I repeat, this is nothing but the Fourier sine series of the given function f of x. And from the theory of Fourier series, we know that the coefficients bn are given by 2 by L integration from 0 to L f of x sine n pi by Lx dx. So from the theory of Fourier series, we can easily solve bn given by equation number 14. Okay. Now let us apply the second boundary condition. Second initial condition. That is the given initial velocity. So what do? So we differentiate equation number 12. So this was the solution which we had taken, the sum of all possible eigenfunctions. So we differentiate each of this term by term. So when I differentiate cos lambda n t, I should get minus sine lambda n t, and then this another factor lambda n here. So this will become minus bn lambda n sine lambda n t. Similarly, this will become plus Bn star lambda n cos lambda n t. So if we differentiate with respect to t, we get this term. The space dependent part remains unchanged. Then you put t equal to 0. T equal to 0. T equal to 0, this will be sine 0. Sine 0 means this term will vanish. This term will not be there. And cos 0 is 1. So what remains is Bn star lambda n. This will remain. This will remain, and sine n pi by Lx, this will remain. So summation n equal to 1 to infinity Bn star lambda n sine n pi by Lx. This would be equal to the initial velocity Gx. Now we also see that this is nothing but a Fourier sine series of the function g of x. And from the theory of Fourier series, we can easily determine Bn star lambda n. So Bn star lambda n is given by 2 by L integration 0 to L gx sine n pi by Lx dx. And now lambda n, we know that lambda n is equal to Cn pi by L. So we substitute lambda n equal to Cn pi by L and then take lambda towards the right. So lambda will divide the right hand side. So when we divide the right hand side by lambda, we get this L and this L will cancel out and we'll get Bn star equal to 2 Cn pi integration from 0 to L gx sine n pi by Lx dx. So the expression for Bn is given by equation number, Bn star, it should be Bn star. So the expression for Bn star is given by equation number 15, and the expression for Bn is given by equation number 14. So when we substitute Bn from equation number 14 and Bn star from equation number 15, we get the final solution. Okay. So it is written here, thus unxt given by equation 12 with coefficients Bn given by equation 14 and Bn star given by equation 15 is a solution of the wave equation that satisfies all the conditions in equation 5, that is the boundary conditions and initial conditions, provided the series equation 12 converges. This will be a solution provided this series converges. And not only the series should converge, and since the wave equation is a second order partial differential equation, so the series obtained by differentiating that equation 12 twice, term by term differentiation with respect to x and with respect to t, and have the sums, it should be equal to this, and the other should be equal to this. So I can say Yugi infinite series to, if I differentiate it twice with respect to x, and if Yugi infinite series to, if I differentiate it twice with respect to t, I should get this expression. And these two series also should converge and they should be continuous. So finally, we have solved the differential equation. What is the solution? The solution is given by equation number 12, and the coefficients Bn and Bn star are given by equation number 14 and equation number 15. So that is the final solution of the wave equation satisfying the boundary conditions and initial conditions. So let me stop the recording here.